Wire arc additive manufacturing process for higher deposition rate and mechanical strength. Abstract wire arc additive manufacturing, also known as WAAM, has always been economical and highly efficient technology which is very suited for producing large and complex shaped metallic components using the process of 3D printing. In past few years, it is widely studied in various fields such as automotive, marine as well as aerospace industries. As WAAM has advantage of higher metal deposition rate, lesser machining cost, higher buy-to-fly ratio and very lesser lead time in comparison to any other powder additive manufacturing processes. WAAM had always been noticed topic by many of the industrial engineers and researchers. If we compare WAAM process over any other traditional manufacturing methods, considering the complex shapes and high buy-to-fly ratio, BTF, WAAM is always proved to be best of them. Therefore, having an advantage of comparatively lesser manufacturing cost, better quality, and a higher efficiency, WAAM became highly used technique for fabricating a component with a much higher metal deposition rate and least material wastage/least scrap. This paper provides a detailed overview of 3D printing of metallic object by inheriting WAAM technique as manufacturing method. At first, the review introduces metal wire and WAAM technique of 3D printing, followed by WAAM systems that are being used to manufacture 3D component, and analyzing which aims to study metal deposition rate and mechanical properties. Keywords: direct energy deposition, DED, buy-to-fly ratio, BTF, additive manufacturing, WAAM, high deposition rate, CMT, GTAW, plasma arc welding, PA, LMD. 1. Introduction. Wire arc additive manufacturing, WAAM, is a process of manufacturing which combines continuous metal feeding in the form of wire and arc welding technique for 3D printing. Although this idea is not new, in last few decades several researchers were working over the use of various arc welding techniques on layer-by-layer deposition of weld bead to production of 3D parts. Therefore, welding techniques such as cold metal transfer, CMT, gas metal arc welding, GMAW, gas tungsten arc welding, GTAW, or plasma arc welding, PA, have been implemented for additive manufacturing of various metals/alloys such as steel, aluminium, nickel superalloys, and titanium alloys. WAAM on the other hand adds to typical additive manufacturing processes with furthermore advantages such as lesser welding equipment's cost, easily available standard metal wires, virtual and non-limited part sizes and a higher deposition rates. In this way, for steel's selective laser melting, SLM, attains metal deposition rates of 0.1 kg/hr, whereas laser metal deposition, LMD, was being able to deposition of 1 kg/hr, but WAAM technology has achieved a higher deposition rate reaching up to 5 to 6 kg/hr. Then again, WAAM showed a few disadvantages when contrasting it with SLM or LMD. In WAAM heat input is higher, that prompts to high residual stresses and bending/distortion. Hence fabricated part accuracy and roughness is lower than that of any other additive manufacturing advancements, and there is always a need of machining step. In addition, the low accuracy causes difficulty in redesigning by the use of geometry optimization algorithms. Therefore, WAAM technique is adequate for manufacturing of large size parts which are manufactured by high cost materials and requires a high amount of machining. It was proven to be nothing that most of the previously done work were been completed over single bead multi-layer arrangement with or without torch waving or lateral oscillation. Single bead layer was able to produce a wall thickness of about 2 mm to 10 mm. For manufacturing walls with a more thickness than this requires overlapping of multiple weld beads adjoining each other. In such kind of overlapping, the center distance between the joining weld beads have a great effect on the surface finish and layer flatness. Previously done researches over multi-bead overlapping showed a result that it is not possible to get an ideal smooth any flat overlapping surface. Various researchers now discovered a new multi-bead overlapping model that determines an optimal center distance for ensuring a stable overlapped bead. In WAAM applications, non-uniform deposited beads can cause cumulative errors along direction of bead deposition that can cause an unstable process. Along with this issue can be solved by real-time monitoring by controlling welding current and arc length, that can result in a better surface quality and lesser material wastage. Up to now, GTAW and PA arc welding techniques were described as more reliable and most suitable processes for WAAM with much lesser problems like excessive heating, porosity, and distortion in GMAW technique. But in both of the techniques the metal wire was not fed coaxially, which thereafter resulted in process variations on altering the direction of weld deposition and sensitivity to arc length. And the fact is that many of the welding system implementing robots requires rotary axis for the positioning of nozzle and matching it with the position of welding that marked its applicability limited. In this work 3 types of welding processes are used, which are plasma welding, PA, cold metal transfer, CMT, gas tungsten arc welding, GTAW. In this PA is the conventional welding technique, whereas CMT and top TIG are advancement of GMAW and GTAW welding techniques respectively. The first reduces the heat input and variations in process by traditional GMAW technique, and the second is the GTAW, coaxial, that improves all over metal deposition rate of the WAAM process. The outcome of the work not only includes capabilities of all the implemented processes to generate high-quality parts. Moreover, mechanical properties were also studied and analyzed for the AISI 316L stainless steel. 2 Literature Review. S.No. Title. Author and year. Publication. Findings. 1. A review on wire and arc additive manufacturing of titanium alloy. Zidong Lin, Kaija Song, Xinghua Yu. 2021. Elsevier. This paper gives knowledge of 3D metallic printing of titanium alloy using WAAM process for metal deposition. 1. 2. A multi-bead overlapping model for robotic wire and arc additive manufacturing, WAAM. Donghong Ding Zhengzi Pan, Dominic Quiyuri Huihun Li. 2015. Elsevier. This paper shows a vastly improved guess to the exploratory estimations when compared with flat top overlapping model, FOM. This is basic in measure, intending to accomplish better geometry, accuracy, and material effectiveness in additive manufacturing. 2. 3. Preliminary development of a wire and arc additive manufacturing engineering. JL Prato Cirque Arat, JL Digesb, AM Chemico. 2017. Elsevier. The primary target of this work is to show the principal encounters in the advancement of a practical metal added substance producing framework based on gas metal arc welding. 3. 4. Additive manufacturing using WAAM with AA5183 wire. 7. A. Horgera, H. Fostervalb, B. Nahusb, X. Renb, M. Eriksonb, O. M. Axelson. 2018. Elsevier. The current review tends to wire arc additive manufacturing of AA5183 aluminum alloy utilizing regular gas metal arc welding deposition on 20 mm thick AA6082T6 plate as support material. 4. 5. A review of wire arc additive manufacturing and advances in wire arc additive manufacturing of aluminium. K.S. DeRieker. 2018. Elsevier. This paper is an audit of WAAM technology, including a brief of WAAM history, status, benefits, and limitations of the WAAM field. A focus is given including the endeavors coordinated towards the decrease of porosity, malleable properties, microstructural examinations, and other important headway in the field of WAAM of aluminium. 5. 6. Effect of heat input on microstructure and mechanical properties of LMG alloys fabricated by WAAM. Chuanchu Su, Zhang Chen, Chuang Gao, Yangfen Wang. 2019. Elsevier. From this paper, it is obvious that parts produced by WAAM CMT have a preferable exhibition over the 5356 regular casting alloys. 6. 7. Development of low-cost production process for prototype components based on wire and arc additive manufacturing, WAAM. Natalia Charnabal, Bert Lauwers, Patrick Van Raymond, 2020. Elsevier. This paper centers around the various strides to be taken to adapt existing GMAW innovation into a moderate and effective WAAM innovation. 7. 8. Investigating the generation process of molten droplets and arc plasma in the confined space during compulsively constricted WAAM. Menguo, Chuanbeo Jie, Jiwi Zhou, Wenqiang Lu, Chuansong Wu. 2020. Elsevier. The paper uncovered that arc behaviors and beads transfer were truly unstable at low-level electrical boundaries, with the features that the beads transfer measurements were huge, 1.85.3 mm, the beads transfer frequencies were low, 223 Hz, 8. 9. Thermal management in WAAM through the CMT advanced process in an active cooling technique. Fernando Matos Scadia, Felipe Ribeiro Tizairat, Leandro João da Silva Douglas Bezerra de Araújo, Ruham Pablo Reza *, Americo Scotti, 2020. Elsevier. This paper gathered that the chance of influencing the thermal cycles and geometries of the resultant preforms with two autonomous thermal administration instruments grows the windows for discovering ideal affidavit boundaries in WAAM 9. 10. Wire Arc Additive Manufacturing, WAAM, Process of Nickel-Based Superalloys. A review. V. Dinakaran, J. Ajith, A. Fatima Yasin Famid Ha, T. Jagadisha, T. Sathish, B. Stalin, 2020. Elsevier. This paper infers that the broad utilization of WAAM actually shows many difficulties, and these should be engaged and settled in explicit manners for various materials to create a functional framework in an acceptable time span. 10. 11. Wire Arc Additive Manufacturing, WAAM, a new process to shape engineering materials. Sudhanshu Ranjan Singh, Pradeep Khanna. 2021. Elsevier. This paper expects to portray the different stage-wise advancements and capabilities of WAAM tech, with an outline on the materials that can be worked upon and some knowledge on the future possibilities of the technology. 11. 12. Ultra-cold wire and arc additive manufacturing, UCWAAM. Tiago A. Rodriguez *, Valdemar R. Duarte, R. M. Miranda, Telmo G. Santos, J. P. Oliveira. 2021. Elsevier. By eliminating the electric flow through the substrate and separating the electric arc from the liquid pool, this new WAAM variation can diminish the process temperatures and increment in cooling rates, without compromising the trustworthiness or deposition pace of the fabricated parts. 12. 13. A review on process planning strategies and challenges of WAAM. Sagar Singh, Satish Kumar Sharma, Dinesh W. Rithad. 2021. Elsevier. The nuts and bolts and essentials of WAAM methods, different significant stages and key interaction getting ready for WAAM have been explained. Moreover, the difficulties and cutting-edge developments in this conspicuous field of WAAM are engaged for the better comprehension of processes and technologies. 13. 14. Metal transfer modes for wire arc additive manufacturing. LMG alloys, influence of heat input in microstructure and porosity. Aldolor A**, Asa Eres AB, F. Vega A. 2021. Elsevier. In this paper, aluminum alloy 5356 is analyzed in the gas metal arc welding, GMAW, based WAAM innovative cycle. From among the different suggested working methods of various makers, 3 working modes for aluminum alloy are analyzed: pulsed GMAW mode, cold arc mode and pulsed AC mode. 14. 15. Investigation of the WAAM processes features based on an indirect arc between 2 non-consumable electrodes. Jiwizhou, Chuanbaojia *, Menguo, Moai Chen, Jinqiang Gao, Chuansong Wu. 2021. Elsevier. This paper confirmed that the solid burning arc kept continuously melting the steel cord. Because there is no modern-day flowing through the droplets and molten pool, the crucial manner function of low warmth input became revealed. 15. 16. Hot forging wire and arc additive manufacturing, HFWAAM. Valdemar R. Duarte *, Tiago A. Rodrigues, Enchelb, R. M. Miranda, J. P. Oliveira, Telmo G. Santosa. 2020. Elsevier. The paper showed that this new version refines the solidification microstructure and reduce texture consequences, as decided via high-power synchrotron X-ray diffraction experiments, without interrupting the additive production procedure. 16. 17. Recent developments and challenges associated with wire arc. S. Srivatsav, V. Jayakumar, M. Sathish Kumar. Elsevier. This paper overviews the imminent studies and traits on WAAM. Additive manufacturing of alloy, a review. 2021. Techniques and frequently used materials for the equal. Common errors which arise at some stage in WAAM were mentioned in this paper, together with the advantages of WAAM. Alloys of aluminium play a key function in the marine, aerospace and car industries. 17. 18. Oxidation in wire arc additive manufacturing of aluminium alloys. Tobias Hauser AD*, Raven T. Reich BD, Philip P. Breeze CD, Yogesh Nalam D, Kaivalya S. Joshi D, Katharina Bella D, Tobias Camps D, Jörg Volpe, Alexander F. H. Kaplan A. 2021. Elsevier. It became located that the arc interacts with the prevailing amorphous oxide layer of the formerly deposited layer and turns it right into a white duplex, crystalline and amorphous, oxide layer. In addition to the analysis of the white surface oxidation, Oxidation anomalies, which occur at low protecting from the environment, have been investigated. 19. Robot-based wire arc additive manufacturing system with context-sensitive multivariate monitoring framework. Raven Rasha B***, Tobias Hauserb, Tobias Kampsieb, Alois Nola. 2020. Elsevier. A WAAM machine is divided into 4 elements: welding supply, kinematic structure, control gadget, tracking system, and an evaluation is performed for every. Requirements are described based totally on those evaluations and further desires in a robot primarily based WAAM setup is proposed. 19. 20. Continuous three-dimensional path planning, CTPP, for complex thin parts with wire arc additive manufacturing. Automediaward EA*, Florian Bugarin A, Cyril Bourdrouil B, Ste Fane Segons. 2021. Elsevier. The manufacturing of those elements with CTPP and numerous numerical critiques have proven the reliability of this method and its ability to produce complex new shapes with an excellent geometrical restitution, difficult or not possible to attain these days. The use of 2.5D with WAAM generation. 2021. Arc behavior in wire arc additive manufacturing process. Pranjal Shukla, Balaram Dasha, Digala Venkata Kirana *, Satish Bukapatnam. 2020. Elsevier. It changed into determined that the bead width step by step multiplied from the first layer to the fourth layer and remained about the same from 5th to the 10th layer. 21. 22. Weld bead modeling and process optimization in hybrid layered manufacturing. Suryakumar S, Karunakaran KP, Bernard A, Chandrasekhar U, Raghavendra N, Sharma D. 2011. Elsevier. According to previous researches, the multi-globule or bead overlapping models have claimed that it is difficult to accomplish an optimal flat surface with overlapped molten metal beads. 22. 3. Experimental procedure. The tests took place in a robotic cell and there was 2 Cartesian machines, Fig. 1. And 3 different power sources were used. Frenius Trans Plus Synergic 4000 CMTR, power source was connected to Robacta drive torch from Frenius. Top TIG 220 DC source and patented torch from the Air Liquide. Praxair EWM Tetrix 400 Synergic plasma source coupled to Plasmatechnic PWM 3508 torch. C:/users /abhir /desktop /kkk.png. 3.1.1 CMT, AISI 316L. 3.2 Top TIG process in WAAM 3.2.1 Top TIG AISI 316L. Mechanical properties were calculated by tensile test specimens which were produced by electron discharge machining, EDM, having a geometry according to ASTM E8-16 standard, Fig. 2. A specimens was tested for studying mechanical properties of the specimen walls in 2 directions, PL, bead generation direction, and PT, bead vertical overlapping direction. AISI 316L specimen was tested as the built conditions. Tensile tests were performed in a model Z100's wick/roll at ambient temperature by applying a displacement rate of 1.6 mm/min and by the use of an extensometer with gauge length of 25 mm. 3.1 CMT process in WAAM. Cold metal transfer, CMT, process is a welding method optimized for lowering the heat input into the metal substrate and it is very common to use it in industrial welding of many steel alloys. Moreover, this work only showed the results obtained for deposition rate of 2,5 kg/h and compared them with those which were obtained by all the other processes. CMT process showed very good results of up to 5 kg/h metal deposition rates with AISI 316L. Though, CMT process produces the bead with a relatively higher aspects ratios, relationship B/W bead height and the width, that could make the process difficult for overlapping and it may cause defects in the component like pores or voids. Regarding the mechanical properties, results showed that properties were dependent clearly over the test direction, Fig. 3. While longitudinal specimens, PL, were close to the least value fixed by the standards, transversal ones, PT, not reaches these limits, which shows lowering yield strength and elongation at break that demonstrates a much more rigid behavior over the traverse direction. Therefore, for the tensile strength tests 3 types of gases were studied, 100% of AR, single bead wall, 50% AR 50% He and 100% of He. It was worth nothing to increase the percentage suppose an increase of the price of the gas. 4. Top TIG is a TIG technology that allows the coaxial feeding of wire that increases the metal deposition rate and providing a high quality TIG process. The major limitation of top TIG technology is that it has a lower deposition rates when compared with CMT or PA. The results showed this limit in 1.5 kg/H for AISI 316L and the current equipment, Fig. 8. This limit resulted from a lesser heat input of the process which was unable to melt the wire when the feed rate increased. Moreover, it is very necessary to care of the aspect ratios that could make difficult for horizontal overlapping. 3.3 Plasma arc welding process in WAAM. On the other hand, the mechanical results obtained from top TIG were situated over the least required and show high homogeneity in both the directions, Fig. 6. PA constricts the arc within the pilot arc, increasing the energy density, so beads produced by this process were shorter and wider, which means they had a lesser aspect ratio. The fact eases the horizontal overlapping, avoiding pores and voids. Mechanical tests were done on the wall generates at 1.5 kg/H metal deposition rate. Moreover, 3.5 kg/H values could be reached with suitable quality. Test results, Fig. 11, shows a high anisotropy between the directions. PL specimens crosses both yield and ultimate strength limits, while for the PT it reaches the limit only for the ultimate strength. In both of the cases, values of elongation at breaking were below the limited values. For results. The results section shows the obtained results that we get from the use of the three processes for additive manufacturing. Results includes, not only mechanical properties of the specimen, but also the capability of each accomplished process that to be applied in higher metal deposition rate for additive manufacturing. Results are classified by WAAM technologies, CMT, PA, and top TIG, and a material, AISI 316L. For conclusions. The work studies various three welding processes, plasma arc welding, PA, cold metal transfer, CMT, and air liquide top TIG for the wire arc AM in the terms of acceptability and the obtained properties. The material that had been studied, an AISI 316L stainless steel. From the results obtained, following things can be concluded. WAAM technique, without considering welding technology used, achieving a good quality manufactured component with a deposition rates of as high as 5 kg/HR in the AISI 316L. The obtained results show that, although WAAM technology was able to obtain the mechanical requirements, the only matter that was important is the choice of the correct welding technique depending over the material properties. CMT achieves the highest metal deposition rates in stainless steel but shows anisotropy in the mechanical properties. And hence, it can be concluded that the CMT process is best for bigger size stainless steel components with a lesser or medium mechanical requirement. Top TIG achieves the most suitable properties for the stainless steel and showed a good homogeneous behavior without consideration of the directions. Although, its lower energy efficiency didn't allow high deposition rates, 1.5 kg/H maximum, and made it necessary for the usage of an active shielding gases mixture. Therefore, top TIG method can be used for the small or medium-size stainless steel parts that have medium or high mechanical requirements. PA achieves a intermediate metal deposition rates for the stainless steel, 3.5 kg/H, with the better properties in both of the directions. Therefore, PA method is recommended for the medium or large size stainless steel parts that have medium or high mechanical requirements. Regardless of the welding methods, parts that were manufactured by WAAM process had shown the anisotropy in the properties that should be taken into account in the duration of design procedure or be heat or mechanically treated during the 3D printing.